Hi, hello.
Hello, good morning. We are going to present today the advanced seepage and structural couple analysis with CivilFEM 218, these new capabilities that we have added. We are going to see four examples and just some of the capabilities that we are having with this new CivilFEM version. We will have some more webinars about seepage and structural analysis in the future. This is just a starting point. With CivilFEM, we can perform advanced seepage analysis, and not only steady state, also transient, with also orthotropic permeability conditions in the materials to determine water table variation, water flow through different soil sections, poor water pressure, and also very important, the impact of this poor water pressure on the stresses on the model to work with effective stresses in the geomaterials, from geotechnical materials, and how these poor water pressures affect in the strength reduction of the materials, density of the soils as well, and just the impact that can have in the stability of the foundations and of the structure. The aim of this webinar is to present these capabilities, these advanced seepage structural couple analysis capabilities, with some examples, and to provide a general overview of these capabilities. If you would like to have more details, you can ask us for a special demo and some more information. So this is a short webinar, only 45 minutes, and we are going to see four examples. And just we don't have much time to see in detail, but just a global overview. Just CivilFEM capabilities are saturated and unsaturated hydraulic material properties, work to determine the water table and the variation of the water table, the potential seepage phase boundary conditions to solve free surface problems, just to determine the water table, the free surface work, the seepage condition through those free surface, and also head at different parts of the models to consider water reservoirs. And also, use these seepage results just as initial conditions to solve a structural analysis with effective stress in the material properties, and also post-processing results. And we are going to have some examples. The first examples we are going to see is an earth embankment dam, that is a loose material dam, and we are going to we are going to perform a drain design downstream to ensure safety, to increase slope stability downstream. And also we are going to perform a reservoir drown down analysis, just to check if, due to the drown down upstream, we will have some slope instability due to this fast drown down. The next example, this will be a 2D model. The next example will be also a pond with that it's the impermeability of the pond is due to clay, a clay liner. And we are going to perform a transient seepage analysis where a crack happens in this clay, and the flow through that crack. And then the last two examples will be a two concrete dams, a gravity one, and also an arc dam, and with orthotropic materials to determine the seepage under the dams. And the last one will be an example with the slope instability under heavy rain. There will be a water table variation, the beginning horizontal water variation here, water table here, and due to this heavy rain, this water table will be increased, and the effect on the slope instability, and also some drains. We will add some drains here for the water table to be reduced, and just to analyze the slope instability under these different water table conditions. Let's start with the first model, earth embankment dam, and it will be a 2D one. So we are going to see this in the okay, we are going to see the first example. This is the model. Well, here first I'm going to show you how to define a new model. Here, if you would like to start, you can define if you are going to do a 2D or 3D model, static or transient model, and structural or seepage. In our case, is 2D, steady state, and seepage. And click OK. Also, we can change from static, steady state to transient here. So the same model can be solved with a steady state or transient. We can modify the conditions. Okay, if I open my model, here I have. As you know, we can modify the graphic interface view. So here I'm going to add entities of the model in one side, the properties and parameters, and the output here on bottom. So well, here we have two different materials: the existing soil and the new soil that we have added, dam. Here for the dam we have the material that we have called embankment. So here in the embankment material we can see this is a porous material, and we can have we can select for orthotropic or not orthotropic material properties. If we click here, we define in X and Y directions the different conductivity values, the permeability values in X and Y directions. I click here, and there is a constant. Also, the conductivity factor can depend on the pressure, on pore water pressure. So we can define it through this table, the permeability that depends on pore water pressure. If I plot the chart, here is the variations depending on the pore water pressure. In meters, here we will have a different permeability. So it means here that when this value is 0 or greater than 0, that is, we have pore water pressure, or a permeability value is 0.1. But in the unsaturated part of the model, this permeability is reduced until we get 0 for values of minus 20 meters for the pore water pressure. So we can use, we said, material properties are pore water pressure material depending properties. So we can define it orthotropic and pore water pressure dependent material properties. Okay, so well, we are going to solve here different cases. The first case is adding. Here we are going to see the loads. We are going to use the boundary conditions for without drain and with drain. So with no drain, these are the boundary conditions we are solving. Here we have the water reservoir, and this is the head of the water reservoir that we have added. These boundary conditions, head, this is equal to 19 meters in this part. So we have a water here with a head of 19 meters. Here, the head of the in this other part, this is 0 meters in this part. And in this zone, we have defined that water can go through the dam and lift the material through this part. So that is a potential seepage phase. So what we do is click here this option that is seepage phase review. It means that a water table will come from this point here and can finish at any point of this phase. So CivilFEM will calculate through an iterative method the starting with a horizontal point, the end of this water table and the water table through this point. So we are going to solve these two conditions with no drains and with a two drain. So with the two drain, the options are, here we can see, is adding here a drain until this point. So it means that water flow can come through these points. And so, well, just the definition of these boundary conditions. After defining these boundary conditions, we just solve both situations. We can solve with no drain, just clicking here, we will solve it. And after solving this, we can solve two drain here. These two options, with a drain and without drain. If I load results of solving these both cases, here we can see a drain. This is the first result we are having. So I'm going to plot an example hydraulic head. We can see here we have from 19 meters that we're defining till 0 meters here. So this is the variation that we are having. Also, we can plot pore water pressure. Just here, it's just with this smooth plot. It's more difficult to find the water table, but we can modify the options here to make it continuous. Use different scale. So we plot here, and we can see, just I'm going to clear the boundary conditions. We can see that the pore water pressure line that is equal to 0 is around this dark blue. So the water table will come through this option, through this part. I can also plot just two colors. Instead of 10 colors, two colors, a color scale, 3 values between 20 and minus 20. This means that 0 value for pore water pressure will be the water table. We can see here how the water table goes from this water reservoir to this point. Just after solving the next load case, where I have added here a drain, if I check that result, to drain, open it, we can see that now the water table comes through this zone. Also, well, selecting the previous one, I'm going to reset the previous options for the colors, and also here range. Now I'm going to plot an example flux in the elements, through the elements, hydraulic flux, the total one, and with arrows, an example. So here we can see the hydraulic flux through my dam. So well, these are typical values we can plot for the seepage analysis. Well, these are only seepage analysis results, but well, the most important for my dam, for the design of my dam, is the slope stability. So I'm going to check slope stability downstream here with these both conditions. So the way to do that, coming here, train, I'm going to open the model. And now with this model, this is a structural model. This is not a seepage analysis. So in this structural model, I can solve it adding first an initial stress state. This initial stress is due to self-weight, and what I'm doing is just avoiding consolidation, soil consolidation displacements due to self-weight. So with this initial stress on the model, this is structural initial stress, I'm adding this, and I'm going to add also the pore water pressure to the model. So I can select the pore water pressure from a drain and from no drain model, just without the two drain, and with the two drain, one of these options. I can select any of these and click here. So the software is considering the initial stress in the model due to self-weight, structural initial stress, and also pore water pressure. So in this way, clicking and selecting these two options, CivilFEM will consider effective stresses in the model due to pore water pressure. I am selecting the result file from the seepage analysis, and with these configurations, I can solve the slope instability analysis. So just solving the slope instability analysis, the way we are solving this slope instability is considering just the strength reduction factor method. So the material model we are using here, the material model is Moore Coulomb material model. So in Moore Coulomb material model, we have effective cohesion and also a variable effective cohesion and also a friction angle. These values will be reduced by the factor, the safety factor, until the collapse of the model. And in this way, we are determining the safety factor. So, we just have to solve. I have already solved the model, so we are going to plot results. If I plot results, here I am going to plot equivalent plastic strains, and when I plot equivalent plastic strains, set range, and here plot again. Here we can see that we are having yielding in this zone, so for this safety factor that is equal to 2, just the slope instability happens, just the sliding surface is being generated here due to this yielding, and if I plot the deformed shape, we can see that the model collapse for a safety factor equal to 2. This is the yielding, and this is what is happening. The next option is solve again the model, but in this case, I'm not using the pore water pressure without drain. I will select the pore water pressure with the two drain. With this option, the pore water pressure will be smaller in this zone, so the safety factor will be increased. In this case, after solving, we can see that with drain, the safety factor is equal to 2.4. And for this value, I have also this sliding surface. So going back to my slides, here we can see the difference with no drains. This is the pore water pressure, the water table, and with the two drain, this is the water table we get from one and the other solution, and the safety factor is increased from 2, and this is the yielding surface, to 2.4, and this is the difference between one and the other. So due to these two drain, I increase my safety factor. Okay. So the next option I'm going to solve, as we saw before, we have solved first a seepage analysis, a steady state seepage analysis. We have solved it twice to determine pore water pressure, and we are using that pore water pressure in the structural model to determine safety factor downstream. The next option I would like to solve is to consider the reservoir drain down analysis, a rapid drain down of this model. So the way to do that is now, I'm going to open the new model. Now what we are doing is solving a transient analysis. We can see here in environment that we have a transient analysis instead of a steady state. With this transient analysis, we have here generate an initial state that we are starting with the previous condition of here a water table equal to 19 meters, and then we solve for 1 hour, 1 day, 2 days, 6 days, 15 days, 20 days, 13 days. And so we determine with the water reservoir is ground in just 1 hour, but we solve the transient analysis to calculate pore water pressure during the next 13 days. So these are the results we get for the pore water pressure. So for 1 hour, the pore water pressure we get is this one. I'm going to plot to modify the settings just for being able to see it. So we can see that just after 1 hour, here the pore water pressure is reduced in this zone, but more the water table is around this dark blue color that comes here until the drains of the model downstream. So for the next results after 1 hour, this is the pore water pressure. 1 day, just we can see it is reduced in this zone. 4 days, water table is coming down. 15 days, water table, we can see now water table is in this dark blue, that it's coming like here more or less. And finally for 13 days, we can see water table is almost horizontal in this zone, and we don't have much pore water pressure in our model. The water table is around between the green and the blue lines here. I generated a video. Also, we can generate here in post-processing, we can generate animations where we select all these steps, and we can plot here different values. We can plot node results, element results, we can plot flux, we can plot difference, and we can generate the video. So I have already generated this video that we are going to see in the slides. Here, what we are plotting is in this orange color. This is the soil underwater table, and this is in blue one is over water table. This is the initial state water table we are having after my designs of the drains here, and we are going to see how this water table evolves for the 13 days. Here we can see that the water table is being reduced, is coming down for these 13 days until it is almost horizontal and I have no pore water pressure in my dam. So this is the evolution. And well, I'm going to analyze just the model. The next step is to analyze the slope instability in the model. So here, what I'm opening here is the structural model. This is my structural model. And what I've done here is the same steps I did in the previous model. That is, when solving, selecting initial structural stress due to self-weight, and also select select here any of these sorry, tells I can select for the pore water pressure any of these seepage results. I'm going to select the first one just after 1 hour when the reservoir is empty. So I have the highest pore water pressure in my dam, and I don't have here earth pressure in the model because I was also solving with earth pressure on the model with the water pressure here. So after, this is the initial condition, but after 1 hour, pore water pressure, just water pressure on my model is deleted because the model is empty. I have the maximum water pressure inside it, and I solve the slope stability analysis using the strength reduction method. So those results that I get in example here, the safety factor I get for this model is 1.4. Okay, it's greater than 1, so the model is okay. I open it and I'm going to plot equivalent plastic strain. And here, well, I can see how this slope instability is developed. I can see just the yielding surface happens here and the displacement of the upstream slope. I've also generated a video with all these steps, and we can plot that video here. We can show this video with the equivalent plastic strains for the different safety factors. For the safety factor equal to 0.7 till 1.4. When for the safety factor greater than 1.4, the model doesn't converge, it means collapse happens. So if we see here the video, here how this yielding surface is developed and the instability upstream happens due to this reservoir drowned out analysis. So, well, we have analyzed the seepage conditions and also the instability safety factor that is equal to 1.4. So as erosion, I have safety factor without drains equal to 2, safety factor with drains equal to 2.4, and also here for a rapid drown down analysis, just for 1 hour, just we have analyzed first the water table variation for the 30 days, the following 30 days, and also the instability safety factor equal to 1.4. Well, this is the first example, which is just it is a 2D model. Close it. I'm going to see. We are going to see the next model. This model, it's similar to that one, but this is a 3D model. In this 3D model, here I have the water reservoir here, and well, there is a line of clays here just for the impermeability of this model, and this is the terrain I have. So, well, if I open the model here, what we are having is two different materials. Here, a material that has a high permeability, and this layer that we have used, the material, this is clay liner with a different permeability. If we see here the materials, the clay liner, here my permeability is for hydraulic properties for saturated and unsaturated, we have this value that the permeability is equal to 1 meter per day. Here I have the table also for the variation between permeability and pore water pressure. That is when the pore water pressure is negative, that is above a water table, the permeability is reduced, but under the water table, when I have poor water pressures, permeability is increased. So just I solve the model with two conditions. The first condition we are going to solve is here, boundary conditions, the transient analysis on my mess. So here is the water table. I have here, I mean, not the water table, the reservoir head in this part, in these nodes. And here the conditions of seepage. It means water comes outside the model through these points. So those are the boundary conditions I'm using. Here you can see I have added a water table of 10.5 meters. That is constant. This is a transient analysis, and it is constant for 100 days. It means I have here water level of water head of 10 meters. Here I have no water level, but the options of leaving here the water. So I have solved transient analysis for here. We can see I have solved first the transient analysis for different days. 1 day, 2 days, 3 days, until 240 days. And how water comes through the clay, it is not completely impermeable, so it comes through this liner and just through this model. I'm going to select one of these results in example, transient one, and I'm going to plot poor water pressure in example. Also, I am going to plot here the settings just without continuous colors. And here we can see that the water table is, for zero value, is between this dark green and light green. So my water table comes through this part, just making like an L shape here. For this option, just and well, I can plot the poor water pressure. Also, I can plot results like the flux through elements with arrows, and I can see, well, how my flux comes through here and all these options. Well, this is the first transient analysis I have solved. The second load case I've solved is adding a crack in the model. So if I plot the boundary conditions, you can see I've generated a crack here. This crack means we have the same head in the other side of the in the inner part of the liner and the outside part of the liner. So we have just communicated nodes from this corner to this other point. We have communicated them with a free flux of water through these two nodes. Also, we could add here a small element with a permeability. If we would like to model a special permeability through this leak, a special through this crack, if we would like to add a different permeability, lower permeability for this. We have added just free flux. If I open these results during this transient analysis for the crack linear, we can plot in example hydraulic flux. We can see here with arrows this flux through this crack, and how my poor water pressure in example just is modified due to this crack. Here we can see in the previous results the poor water pressure had almost like an L shape, and now here we have other shape just for this poor water pressure. If we go to this to the slides, and we see the transient results, transient seepage results. This is the first option without a link, without any crack in the clay. Here we can see how the water table, that is this one, the line between dark and light blue. This is the water table that is evolving for 240 days, and this is the final result we get for after 200 days. After this, we add here crack in the impermeabilization of the model, and we solve it. We start the model with this condition, this previous poor water configuration. We start on this, and we see just the seepage results through the model, how the pore water pressure is increased, the water table also is increased, and just different results through the model. So as you can see, we can solve also transient seepage analysis with different model configurations and those results. Well, next examples we have are concrete arch and gravity dams. Two dams we are going to see. This is the one, the gravity one, and this is the arc one. So if we just go to the model, I'm going to close this one. If we open the first model, we can see, well, we don't have much time to see these models in details, but just here we can see that we have here the dam, the soil, and very important, in this soil we can have orthotropic values, because we can have different seepage directions. So we can model the material here, granite in the soil, the porous material. It is very important to consider orthotropic results and different permeability in different directions with different table. So, well, and also here, what we have defined is in the model is what we have defined is different boundary conditions. So here you can see on the mesh that we have added here a water table, a water reservoir up to this level. And downstream, we have the river with this other level. So we perform a seepage analysis and calculate the flux under the dam with all those results. If I plot any of those results, I'm going to just select the soil. I'm going to plot, in example, hydraulic head in the model. Here we can see, and just we are going to see one option that is performing a cut in the model. So just in the view options, here view utils, I'm going to perform a clipping plane in the middle of the y direction. So here y to the plane, and well, here we can see the hydraulic head in one side of the dam that is equal to 240 meters, and the other one that is equal to 163. So, well, we can also obtain any other type of pressure under the dam, just pure water pressure on the dam, also flux, any other result. Well, the next model we are going to see is this one, the arc dam. Here you can see this is the geometry we have imported: water table, soil, and dam. And well, this is the mesh we get for this model. We don't have much time to see in detail this model. This is equal to the previous one, but I would like to show you an important improvement on CivilFEM for this 218 version, that is a hybrid mesh. in the mesh configurations, we can mesh with parasolid and hybrid mesh. It means that it will mesh with tetraedric and quadrangle elements, depends if it is possible or not. So if I perform also a cut in the model, example in X and to the cut, we can see that CivilFEM generates triangle-shaped elements when it is not possible to mesh with quadrangle ones. So CivilFEM mixed both of them to perform a better mesh here. Well, with this option, we can see through the model how CivilFEM generates triangle-shaped elements, transition to quadrangles, and just against triangles in the shape. With this option, it's good because for these big models, CivilFEM can reduce the number of elements and nodes with this hybrid mesh. Okay. So well, in this model, we also obtained the same type of seepage analysis results to analyze seepage under the dam and pressures over the dam due to this seepage analysis. We are not going to see it because we don't have much time.
Yeah, we will have another webinar because this type of tools requires a lot of of time to show you all the new capabilities, and this is just a first approach to seepage webinar.
Well, the next example we have seen. This is an example where I just solve the structural model, but without seepage analysis. Instead of solving seepage analysis to calculate pore water pressure and then use those seepage analysis results in the structural model for the coupled analysis, just to consider effective stresses, what I'm doing is define water table. For the water table definition, I'm going to define 3 different configurations. The first one, the initial water table due to the river here in the two of this slope. So well, due to a heavy rain, this water table comes from here is increased. So the pore water pressure is increasing this, and due to the effective stresses, the slope instability, the slope stability safety factor is reduced. Then I add some drains in my model. So here you can see the pore water pressure is reduced in the instability part of the slope. So well, you can see that we can solve these 3 models, 3 results. If I open the model, here what we are doing is defining the initial conditions water table. So we can define water table here in loads, seepage initial conditions. Clicking here, we define the initial water table. The initial water table can be defined by Z axis or the orthogonal to a vertical axis. We can select our vertical axis, in my case is Z axis, orthogonal to that, and define my water table height. In my case, 0 Z value is here on my building, on the bottom of my building, and minus 83.5 is here the river water table. So I can solve the model, the structural model, with this initial water table. And also I can generate a variation of this water table using the geometry, that is selecting different planes. So I have 2 different configurations. I've created this plane in my model. This plane is the water will be used for the water table after heavy rain for several days, heavy rain here on top, and this will be my new water table. So with this water table, I can calculate also the safety factor for this slope instability. And also here I have defined, if I comes here to the geometry, I have also generate other options for the water table, that is here in my model. That is with drains. and with just that is here my surface, sorry, with drains. So here you can see I've generated two different planes, one after the heavy rain and one after adding some drains here on my slope. So I'm using these planes. Now I'm plotting planes in the model. And if I plot the element mesh here, well, you can see I have solved three different configurations: water table, horizontal water table, a water table after the rain that comes with this shape, and a water table after the rain with drains on my slope. So three different water table configurations. And the way to select the different water table configurations is coming here, initial configurations, and select by clicking. And I can select this one or this other one and modify the water table configuration. So with these other configurations, after selecting it, I solve the model and I solve the slope instability analysis. So, well, one of the results I get with a horizontal draining example, I can see that CivilFEM calculates first pore water pressure, and plot it. This is the progress slides. It is a big model and goes slowly. So this is my pore water pressure with the initial configuration, and also the pore water pressure for due to the heavy rain. Here we can see that due to the heavy rain on the top of the slope, the pore water pressure and the water table is increased in this zone. Here you can see, and solve the structural analysis. So here, if I go to my slides, you can see that we have the water table definition. We define it in three different ways. This is the pore water pressure. This pore water pressure will affect to my effective stresses, and we calculate the slope stability. Here we can see at the video of the slope stability due to the safety factor. When the safety factor is increased, we can see that the sliding surface is developed and the instability happens. The safety factor we obtain is equal to 1.6 with horizontal water table. That safety factor is reduced to 1 with the rain, and is increased again to 1.4 with my drains on the slope. So with this seepage, with this water table definition and structural analysis, we can design our models. Well, these are all the examples we wanted to show today. For future webinars, we will see consolidation material models, just to solve a mix between camp clay and seepage analysis, where the water table affect to the consolidation problems to calculate transient analysis and consolidation during the time with these material models. And we will see other material models different that camp clay than more Coulomb that we have used for this model. So, well, as a summary, CivilFEM seepage structural analysis features, we have saturated and unsaturated hydraulic material properties that they can be orthotropic. The potential seepage phase boundary conditions to solve free surface problems and to calculate water table. Also, steady state and transient seepage analysis with initial condition from steady state previous analysis. Also, we can consider instead of solving seepage analysis, the user can define a water table and consider effective stresses in the model to in the structural for the structural results for stresses, yielding, the displacements, and settlements on the model. So, well, this is the overview, the first overview of the advanced seepage structural analysis of CivilFEM. And, well, with this overview, if you have some questions, you can ask us your questions, or you can also ask for a special demo for we can perform for you. Also, if you would like, you can download the demo version of CivilFEM, a demo version that you can use to check it.
Yes, please. Of course, there will be a short a survey after this webinar. It will help us a lot if you complete it. It will take just a minute, so we can always show you the best capabilities to you.
So, also we have the website civilfem.com. Here you can check next webinars, CivilFEM videos, CivilFEM results, and also ask for information. Also, you can contact us, or also we have partnered and software distributors all over the world that you can connect with any of them for extra information. Okay. Well, thank you very much for your attention, and just thank you for fulfilling the questions we are having, and just you can contact us whenever if you have any extra questions in the future. Thank you very much.
Thank you.